Here's the next thing we need to talk about. And that's how a magnetic field and a current can produce a torque. So what I have here is just your basic double-A battery and a magnet that's pretty strong magnet that's attached to the bottom of it. So what this is, all this is a wire, piece of wire, copper wire, and I've bent some loops into the bottom of it. And I'm going to put this so it rests on top of the battery. And then what's going to happen is that because the battery is connected to the bottom of the magnet, then what's going to happen is that that's going to touch that magnet. That's going to allow a current to be completed. So now I'm going to have a current moving through the wire. But that's also going to be in the presence of a magnetic field, which hopefully makes it spin. But this is real finicky. Like, it has to be able to just barely touch the magnet, but it can't touch it so much that it creates so much drag that it doesn't spin. So I think I got it fine-tuned, but I make no guarantees.
What?
Okay?
Magic. Torque. Burning.
It's torque, right? So how do you know that there's a torque acting on the system?
Moving.
It's moving, it's spinning, right? Because that's why I said this thing is extremely finicky. Now, since it's moving in this direction, we know there's a torque, right? So if you're harking back, what do you need to calculate torque? Force and radius, right? So this won't work if I just have the battery, because I have to have two things to create this torque. I have to have a magnetic field, which is what the magnet is providing, and I have to have a current. So if I try and do this with a dead battery, guess what's going to happen? Absolutely nothing, because I'll have the magnetic part of it, but I won't have the current part of it. Or if I hook this up just to the battery, to the positive and negative terminal ends of the battery, that won't work either because I don't have a magnetic field. So I have to have both of them in conjunction to create that. Now, hoops and magnetic field get a little bit sketchy. So let me turn this off and go back to the other one. Hold on, give me a second.
Wait.
Thatcher, that's a question. Yeah, that's called an eyebrow.
What?
On 21, is the north magnetic pole the actual north pole or the south pole?
Oh, that's the South Pole.
Alright, thanks.
It's counterclockwise.
I don't know.
So what would the answer be?
What do you think the answer is on 21 hypothetically?
Hypothetically.
What would you say?
Hypothetically,
What
it's
would
either
you say?
clockwise or counterclockwise.
That's a 50-50. What do you say on that 50-50?
If you were to answer the question,
If you were to
what would
gamble,
put?
Maybe really that's 60.
Hypothetically.
Would you put it on red or black?
it's clockwise. Wait, it is clockwise. Yeah, we got clockwise.
Because no matter
Yeah, you
what
stupid, it's clockwise. It's above it.
the velocity's going.
Dumb. It's clockwise?
It's clockwise.
Okay.
On 23?
That means the other graph's also.
21.
Yeah, that means the other one is exact.
Because look,
They
it
were
says
above,
above,
it's
it's like, think of your in the earth, and you're looking above, you got South Pole.
Oh, okay.
Yeah,
21.
I think that's a poorly written question, personally.
Oh, I really don't care. On the three multiple choice questions on the other sheet, before I forget, none of your answers should be B.
God, if you said D, I was gonna hit.
Oh, no. No, D is a viable answer.
Oh, okay, good.
What about A, B, or C though? You got D.
Can't answer that question.
Yes, that means,
You
that
just
means
don't know,
yes.
do you?
That's about, there's only 3 questions.
Oh, no.
Oh. Hey, what about the what about the 4 multiple choice on?
Oh, no, we're done.
No.
Connor has burned that bridge.
What?
Well, Connor burned that bridge.
What bridge?
Connor.
No, no, D.
What was the bridge made out of?
Relations.
Yeah, that's actually a valid
Calculate the
point.
gravitational.
Anyway, so any other questions on that assignment?
Can we talk
31
about
to 34?
46, please?
We can talk about it. That's a good question, actually. I like 46.
Darts are out. Okay, that's so accurate. That's helpful. I can never remember which one it is.
46.
You said 46, Sydney?
Yes.
Okay, so 23 was a default.
That's a good problem.
How is it into the page?
So you were
How is it into the page? How is it into the
because
page? You're a fool, buddy.
electromagnetism, that's I can never remember which one is which.
Where's the picture?
I was right the first time. I so was
Okay, Sydney,
Has to go into the page.
The right answer.
let's start with this idea.
That's your left.
Let's start with the electron. Is it an electron or a proton?
Electron.
It's an electron. This is gonna be a key part of the story. Okay? It's an electron. Now, for now, don't worry about the magnetic field. This is a relatively simple problem if you go back to the old days when all you had to worry about was electric fields. So, the whole part of this is that you know the velocity, pretty close to the speed of
Let
light,
him explain.
1.0 times 10 to the 7th meters per second. And you got the plates. The plates are separated by 1 centimeter and are charged at 200 volts. So, you got your voltage, you know how far apart the plates are separated. So, the question is, what magnetic field and strength will allow the electron to pass between the plates without being deflected? So start with this idea. Don't worry about the magnetic field. Just focus on the electric field. What's the electric field going to do to this thing? It's going to force it up or make it bend down? It's going to force it up. So the electric field wants to deflect that electron upward. Okay? Now, do you have enough information to find the value of the force created by the electric field?
Yes.
Yes. Fact, right? You know the value of no, you're trying to find the value of the electric field. But you know the voltage, and you know the distance. So, based upon that, then on 46, you can go, oh, E equals V over D. You can find the value of the electric field, then you can set that equal to the force. So, the force from the electric field has to equal the force from the magnetic field, right? That's the only way this thing is going to balance out. So you can find mathematically the force from the electric field. Now, then you can go, oh, QVB equals the force from the magnetic field. Okay? So, on 46, the value of the magnetic field, if you're in Teslas, should be a nice even number times 10 to the minus third.
I agree.
Okay? Like that, Preston?
Yeah.
Okay. On now, the question is what's the direction? So if the force from the electric field
It's 2.
is driving it up, the force from the magnetic field has to drive it down. But it's an electron. So the electron is coming this way. You want a force that's going to push it down. So which direction does the magnetic field have to act? Up, down, into the page, out of the page. No!
Into the page.
Your magnetic field is only going to do one of two things. In this problem, it's either an innie or an outie. Okay, that's it. It's either an innie or an outie. So, it's an electron. It's going this way. You want the force to act down. Which direction does your index finger point? Inward. It's an innie. Okay? It's an innie.
Because electromagnetic.
On 48, that first answer should be around 1400 amps. And your acceleration, again, be very careful how you answer this on 48C, is a little bit more, excuse me, the velocity. Because you got to find the acceleration and then use that equation. Your velocity on 48C should be more than my age, but not by a whole lot.
In between 56 and 60.
In between what?
56 and 60, that's what I'm guessing.
In between what and what?
56 and 63.
No.
No, he's saying that's
On
how old you are.
48C.
I'm saying that's how
He's saying
old you
that's
are.
how
That's what I'm
old
saying,
you are.
that's how old you are. We're just,
No,
yeah.
we're nice.
My previous hypothesis.
Okay, did that answer that question?
Yes, very much so, thank you.
Okay, are we good? Staple the questions to the back. The photocopy sheet, staple that to the back. Get that handed in.
I don't suppose we can do about.
I know it's just really slightly over the universe, but
Oh, it's because our,
Yeah, that's not right.
it's a micro.
Electromagnetism, the way it's at right angles.
Huh?
They want to know how bad that homework is tonight.
It's not bad.
Really?
No, there's not even any problems out of the book.
Is that good or bad?
He says it's not that bad.
it's a physics miracle. No, but remember
Okay,
last time
now
that we
what
had
am I not
their
doing
physics one?
about this? Because I probably made that number too big. Right.
Like 50 bajillion words.
Now
Yeah,
do
no,
that.
they're gonna be like that.
And then do that.
It's even funnier.
That gets me.
So you would have problems.
Wires going like
Okay, now what am I doing?
Every part has 5 subparticles.
because that's the way it's supposed to be.
Hey, twinsies.
Twinsies.
I know where they're at, it takes me.
Okay,
But it'll move in.
so let me give you this hypothetical question. Speaking of making hoops turn. So let's say that you've got a hoop, okay? And you have a current moving in it. So the current's going like this. And what I want to do is I want to put it in, it has a current. Without the current, nothing's happening. So it's hooked up. You have a current going through it. And you want this thing to spin clockwise about the positive x-axis, okay? So here's your positive x-axis going like this. So you want this thing to spin clockwise around that positive x-axis. So let me give you a hint on how I handle this problem. Luke's circles get a little bit weird. But so what I do is I envision it as a square, because squares is going to make this easier to see. So the current is going in this direction, okay? Current's going around like this. Now, let's just think this through. Forget about the magnetic field. Here's your loop. And you're like this, and this positive x-axis is coming in like this. and you want it to spin clockwise around it. So what are you gonna do on this side of the loop? Are you gonna push it down or pull it up?
Gotta push it down.
That's gonna get pushed down, and the other side has to get pushed up. So if this is going to happen, if I want this thing to spin clockwise, I want this side of that hoop to be pushed down, and I want this side to be lifted up. Okay? Now, this is the current by the traditional value of current. So let's look at some options. Okay? I want it to spin this way. So if you use the right-hand rule, okay, because this is current, right? This is current. So let's start with this side over here. Okay? It doesn't matter which side you pick. I'm just going to start with this one. Okay? So the current is going in that direction. And I'm going to look at, here's that axis that it can spin about. So I'm going to look at this little bit over here. So the current's going this way, right? Which direction do I want the force to act? I want this side to get pushed down. So if I take my thumb and point it in that direction, right? And I want this side, okay, so here's this section. So current's going this way. I want that force to be pointed down. So on this side over here, where do I want the magnetic field to go? Parallel with this wire or parallel with the end wire?
This wire.
The first wire up there. So my first inclination is to say, I want the magnetic field to go in this direction. Now, let's think about this. If the magnetic field is going in this direction, let's just say hypothetically that we're right. What impact will that magnetic field have on that portion of the wire up there? Do not make this difficult.
Nothing.
Nothing. Why?
Parallel.
It's parallel. So the magnetic field isn't going to interfere with this section of the wire or with this section of the wire, if that's the direction that it's going. Okay? Nothing's going to happen. It's just going in this direction. Now, let's look at this section over here, right? So I want this section over here to get lifted up. So now, if the current is going this way, so let's see if it works on this side. So if the current's going this way, and I assume that the magnetic field is going in that direction, what's it going to do to this side of the wire?
Lift up.
It's going to lift that side up. So because I can't have this thing going in opposite directions, I have to have the current, a magnetic field that's going to make both sides go in the direction that I want it to go. Otherwise, it's just going to like bend it or it won't spin. So if you look at the current going this way, and we assume that the magnetic field is going in this direction, so don't worry about anything else. Just focus on this little bit right here. So if I take, because it's a current, I got my right hand going like this. I think the magnetic field is going to be going in this direction. Guess what? That's going to lift this side up, and I'm going to make it spin.
Yeah.
So the magnetic field needs, no matter how you look at it, needs to go along that positive x-axis. Charles.
What are we spinning and why?
Okay. So what we're trying to do is make this wire spin, and you're told that I want to make it spin like this in a magnetic field.
Why is it a square there?
Because it's easier to visualize it as, personally, I visualize it as a square than a circle.
Okay.
Because if I can make it, if I can figure out the direction on the square, then the same idea is going to work with the circle.
Okay.
Okay? It's just easier for me to see it that way.
Yeah.
Okay? So all the square is a whole bunch of like little squares, or the circle is just a whole bunch of little squares. So if I can figure out, that's just my own thought process. I think it's easier for me to see it if I do it as a square than a circle. Okay. Just so what you want to focus on is that if if the magnetic field is going parallel with the wire, you won't have any torque at all. It's only the sections that are at right angles to that magnetic field. That's where you're going to get a torque. So figure out which way you want it to spin, because if you're gonna make it spin, one side's gonna be lifted up, the other side has to be going down. Figure out which direction you want it to spin, start with that and go, okay, current's going this way. I wanna make that side lifted up, that's gonna tell you which direction that magnetic field has to point. Okay, now the next thing I'm gonna do is gonna settle this whole debate about whether it's electrons or protons that move, okay? So, I'm gonna look for this big complex problem to settle this debate once and for all. It's known as the Paul's effect. So, let me draw a picture here. Give me a second.
What am I?
What am I?
Yeah. Where am I? What am I? Who am I?
Yes, those ions right there.
I don't think therefore I'm not.
I think I'm looking at the wrong piece during the choir. I'm looking at a bunch of sheet music.
What are you talking about? We don't do choir. This isn't relatable. We don't do choir.
I need to ask what piece are we
I know you're done with these. This is last unit.
It's
Is
not
that a capacitor or a battery?
that bad.
Looks like a gun.
Okay.
It kind of
That's the gun.
is.
That's the bar. That's me over there.
No, obviously it's a football player.
It
Kind of is.
Conducting, I call it conduction plant.
Plate. I'll call it a conduction plate. God
Okay.
created on the 8th day. Saw his creation was terrible. Destroyed it. That's why it's not in the Bible. No.
Okay.
God.
Now, so, here, let me paint this picture. You've got a small conducting plate, piece of iron, silver, whatever it is, something that will allow an electric field to pass through it. You have it hooked up to a battery, okay? And the plate is in an external magnetic field that's going into the page, okay? So I want to look at what's going to happen in two scenarios. If it's positive charges, or if it's negative charges, okay? So the first scenario I want to do is I want to assume by the traditional idea that it's positive charges and the current is going in this direction. So these are positive charges entering this side of the conducting plate. So let's start with this. If it's positive charge, don't worry about the magnetic field. Do not let the magnetic field be part of the story, right? Do not let the magnetic field be part of the story. If you have positive charges in this side, and it's a complete circuit, what's the direction of the electric field inside the conducting plate to move positive charges to the other side? It's either left or right. Will Stanley.
Repeat the question.
Okay. I want positive charges to move from the right side of that conducting plate over to the left side. Okay? What's the direction of the electric field inside the conducting plate?
Conventional or real?
Is it to the left or to the right? Connor S.
Does electric field go from positive to negative or negative to positive?
Are we talking conventional or actual?
Oh, is it what?
This is a current. Just focus on the electric
I think it's
field.
I think it's front.
So how do you define the direction of an electric field?
I never figured that out.
Based upon what test charge? Positive.
Go right to left.
So I'm gonna make a positive test charge move from the right to the left. So what's, yes, because, right, so to speak. So my electric field
Because
is moving to the left. Cool? Because that's the direction positive charges are gonna move. Now, because we have to establish that first. So here's the next thing. Now we're going to talk about the magnetic field. You have an external magnetic field. Is that going into the page or out of the page? Into the page. So if, this is a huge if it's positively charged particles that are moving, okay? If it's positively charged particles that are moving, the electric field is going to point to the left. If you have positively charged particles that are moving in an external magnetic field that's going into the page, which direction are those positive charges going to move? Downward or upward?
If we got it. Down.
Down. Because if I take my right hand and move it this way, the magnetic field is going into the page, my fingers point down. So if, this is a huge if it's positively charged particles, the magnetic field is going to force those positive charges down towards the bottom. Okay? So positively charged particles would collect towards the bottom. Now we're back to a new electric field. So horizontally, the electric field points to the left. True?
True.
Now, if I force positive charges also towards the bottom, what's the direction of the electric field that's generated vertically based upon the fact that you stacked a bunch of positive charges at the bottom? So don't worry about the horizontal motion. If I put a bunch of positive charges down here, what's the direction of the electric field in that conducting plate based upon the fact that there's positively charged particles towards the bottom? Is it going to point up or is it going to point down? It's going to point up. Why?
Positive test charge.
Because if I have a positive test charge and put it towards the bottom, it's going to get repelled and it's going to go up. Okay? So if it's positively charged particles, you're going to see two electric fields. You're going to see one electric field that's going to point to the left, and you're going to have another electric field that's going to point upward. Okay? So if it's positively charged, you're going to see two electric fields. One to the left, one pointing up towards the top. If it's positively charged particles. Now, situation number two, we're going to have the exact same thing. Same battery, same external magnetic field. Now, I'm going to have electrons moving across the field. Okay? Now, if it's electrons, what's the direction of the horizontal magnetic field in this row? Worry about the magnetic field, just focus on the electric field. Is the electric field still going to point to the left? Or is it going to point to the right?
Still to the left.
So to the left, why?
Because if the electrons are going to go to the right, then a positive test charge will go to the left.
That's right. So if electrons go this way, protons are going to go the other way. So what that means is that if that electron is going to go in this direction, okay? So what that means is that you're going to have the negative end of the electric field here and the positive end of the electric field here. And it's just what Deacon said. So the electron would want to be repulsed by the negative and it'll move over towards the positive. If you put a proton in here, a positively charged particle, it's going to be repulsed by the positive and attracted towards the negative. So in both situations, whether it's electrons or protons, everything stays the same. The electric field, based upon the horizontal, is still going to point to the left. But now let's talk about what's going to happen with the magnetic field. So I got an electron going in this direction, right? The magnetic field is pointing in, so the force is going to be pointing downward, if you use the left-hand rule. So if it's electrons, it's the electrons that would get forced down towards the negative end of the plate. Now, here's the last step. If the electrons are forced to the bottom of the plate, what's the vertical direction of the electric field?
Must be down.
Downward. Why? So a positive test charge would go down. So if you release a positive test charge, it would point downward. So the fundamental difference is the direction of the vertical electric field. So if it's electrons moving down this way, it's the electric field is going to point downward. If it's protons that are moving, the electric field points up. Turns out Franklin had a 50-50 shot. He guessed wrong. So if you actually do this experiment, what happens is that you do see those electrons being forced down, so the bottom of that plate becomes negatively charged. So what that did, this is a relatively simple experiment, but what that did is prove, the only way this works, that we see the movement of this electric field, is the fact that the electrons get pushed down, it changes the direction of the electric field. So horizontally, it's the exact same. Vertically, the electric field switches places. Okay, so, with all that said, okay, that's a bugger bit. I thought
Why
I
do we
was
still
gonna
use
put that in.
conventional then?
So, there's no problems out of the book, it's just these 5 questions, okay? And some of them are even like multiple choice. Actually, the vast majority are multiple choice. So, or gambling, as Connor S. would put it. So let me kind of explain what's going to happen. On problem 1 and 2, you have 2 parallel wires. The current is going in opposite direction, and one has a current of 2I, and the other one has a current of I. So the currents are not the same, but they're parallel wires. So what you want to do, the first part of this is just multiple choice in terms of what's the direction of the magnetic force. Do they retract? Do they repel? If you want to do the circles and figure out what's happening with each one, that's cool. So you wanted to, on number 1, you wanted to determine the numeric value for the force per meter that exists between the wires. So what you can do on number 1 is basically use that equation that you just had. Force equals B mu naught I, or B mu naught I1, I2, L over 2 pi R. And you can find the total amount of force. But it asks for force per meter. So what the easiest thing to do is say, okay, this is how much force there is, and then look at this and go, okay, hey, what's the length of the wire? And then you can say, that's force per unit of meter. Then on number 2, it says if the wires are 0.5 meters long, what's the total force between the wires? So if you have the force per unit, let's say the force per unit is 10 newtons per meter, and you have a half a meter, multiply it by the length, the meters cancel out, boom, you have force. Number 3 is a question with a hoop, and you're trying to find the direction of the magnetic field to make it spin. Again, if you want to visualize that as a square hoop, that might help. So if you look at how I worked that problem, literally that's what I did. I drew it out as a square hoop. Number 4 is basically the question that I just asked. Okay, I literally just completely worked question number 4. I suggest that you rework it and make sure that you understand it. Question number 5, you have 2 parallel wires. And the current is going in the same direction. You want to find the net force at a point 1/4 of the way. So I'm going to be very, very reluctant to believe that you chose this answer with no work. I want to see at least some calculations of how you got this answer. This is not, oh, I just guessed kind of thing.
Gambling.
Facts.
Do we need to do work on another piece of paper?
No, you can do it all here, okay? You can do all the work on here. Okay, Danny, shut down the camera.